Okay, welcome to Chapter 5, a survey of probability concepts. Basically, this chapter we're going to get into the basic rules of probability theory. We'll get into what's called the addition law, some multiplication laws, conditional probability, and Bayes' theorem. And along the ways, we'll walk you through some formulas and some, how to test for dependency and so forth. And then later on, I'll also give you some other examples on either a separate PowerPoint or on a video, just kind of walking you through some other illustrations to, supplement your textbook. Okay, to kind of start you off with, the concept of what they call a probability, it's basically the likelihood that an event will occur. And notice you've got the two extremes. Either it's not going to happen, again, let me put it back to red. It's either not going to happen, which in that case, the likelihood would be said to be 0, or it is sure to happen, which is said to be 1. But notice the range is always between 0 up to 1. And just to make a couple notes, you can never go past 1 and you can never go below 0. So therefore, you should never have negative probability. So you're basically restricted between 0 to 1. Now, in the next couple of slides, what we'll talk about is now that you kind of get the idea what is a probability, the thing you got to realize is before you can actually assign a probability to an outcome or to an event, you really need to know how many possible outcomes are there. And I'll talk about that, and they talk about how you come up with the outcomes. But before you can actually come up with probabilities, you first really need to know your outcomes. Okay, so here they talk about different ways to assign probabilities. You've got what's called the classical method, which is equally likely. You've got the empirical approach, which is, I like to refer to this as I'm going to write this out, as your relative frequency approach. I like to use that as rather than saying empirical, because later on we do talk about empirical rules, and that's a little bit different than this. And then the last one, obviously, is what they call subjective probability. Okay, and so just to kind of walk you through this, I am not going to test you on how to calculate counting rules. Later on, they have the combination and the permutation rule. I just want you to review them just to be knowledgeable that they exist. But basically, one rule is it's the multiplication formula. I often refer to this as a multi-step rule, and it's where basically, as long as you have a certain number of ways of doing one thing and a number of ways of doing another, you simply, it's a multiplication rule. I'm going to walk you through an example on the next blank slide. So in this case, they talk about you had 10 shirts and 8 ties. To get the total number of outcomes, you would take 10 times 8, which in that case would be 80. Okay, and another example of just like a multiple step type of rule. Let's say we're going to toss a coin, okay? In fact, let's say we're going to toss a coin 3 times. So hopefully you can agree that if you tossed it on the first try, there would be 2 outcomes, 2 defined outcomes, a heads or a tails. If you tossed it second time, if this is our step process, you get another 2 outcomes. And let's say you tossed it a third time, there's another 2. So notice for each step of this experiment, we have 2 defined outcomes for each step. If we wanted to figure out what's the total number of outcomes, we'd simply take 2 times 2 times 2, and we get 8 different outcomes. And then what I like to do in my class is I like to kind of just draw a tree diagram just to kind of help you visualize that. So let's say, for example, this is how this would look. You get, on the first toss, you could get a heads or a tails. On the second toss, you would get another heads or tails on each side, right? And then finally, on the third toss, you get a heads or tails on each of them. So notice how it's branching out all of a sudden. And now let me list all my outcomes. So for example, here we go. You could get heads, heads, heads. That could be one outcome. We could get 2 heads and a tail. That would be another one. We could get a head and 2 tails. That's a third one. And then we could get I guess I missed one. I'm sorry. We could get a head, tail, head. I'm sorry, I missed that one. So here's your 4 first outcomes there for just the head side. And then you could start with the tails. You could get a tail, 2 heads. You could get a tail, head, tail. You could get 2 tails and a head, and then obviously you could get all tails. And if you added these up, there's 1, 2, 3, 4, 5, 6, 7, 8. There's your 8 different outcomes. Now, I'm going to leave this up because later on, eventually, let's say we know our outcomes. Remember, because this would be considered an equally likely scenario, so this would be a classical approach, right, to assigning probabilities. I'm going to write this here, but you'll get it later on as well. The formula for assigning an outcome for a classical probability is simply 1 divided by n. So if n is equal to 8, each one of these outcomes would be defined as a probability of 1 over 8, which is an equally likely chance of occurring. So I'm just going to write 1 over 8 for all of these, and then I want you to make a note. If you were to add all these up at that point, you would get 8 over 8, or 100%, and that's kind of like a rule. The sum of all your probabilities should equal 1 or 100%. So I just wanted to kind of throw this in here as an example. I always do this in my lecture classes when I talk about the classical approach to assigning probabilities. And a coin toss is a simple example that most people can relate to. So I'm just kind of giving you just an extra example of how to apply the multiple step rule. And then once you get your outcomes, how to assign the outcomes based on the classical formula, which is 1 divided by n. And I'm just going to mention these. You're going to have a permutation counting rule where they talk about how order is important, and you've got your factorial calculations. I will never ask you to do these in terms of calculation. You can read about them, but this is how they come up with how many, the odds of winning the Powerball, for example, or a lottery. This is the formula that they would use to figure out those outcomes. And the same thing with the combinations. Notice it's just order is not important. It says without regard to order, but it's a very similar calculation to the permutation. We will do some of this with our binomial distributions, but because most of the calculations get so large, we're actually going to use probability tables. So you're not going to really have to worry about doing too much of this manually, but you can read about it if you're curious about just the basic idea of how it works. And I did skip through a couple of those. I think they were good enough you can just read about them. But I do like this slide where it just kind of gives you a summary of the different approaches to assigning probability. And notice the objective approaches are it's either classical or relative frequency type, or the subjective, which is sometimes you base it on whatever you have or your gut feeling. But we'll use a little bit of all of these as we go through the upcoming chapters. Okay, and just some basic definitions. If we talk about what is called an experiment, it's basically a process that leads to the occurrence of one or several different possible results. Tossing a coin could be an experiment because it does lead to what they call outcomes, which are results of an experiment. So for example, if you tossed a coin, the result would be a heads or a tails. And so you have what's called the experiment, you have the outcome, and then the event is basically what they say is a collection of all these outcomes from your experiment. And they give you some examples you can kind of go through down below. But just remember that eventually, once we get the outcomes, that's then when we start talking about assigning the probabilities. Because again, you always need to know outcomes before you can get to the probabilities. Okay, some more basics here. So notice you have what's called the complement rule. And this thing down below is called a Venn diagram. Notice how, let's say you have event A, and then you got this little squiggly line and then A. I like to use an A and then like a C to represent the complement. But the basic idea is let's say, for example, that event A had a probability of 0.70, okay? To get the complement of event A, you'd basically would take 1 minus 0.70 and you get 0.30. So basically the complement is always subtracting that event number from 1 to get basically everything else, okay? So again, I'll just give you another one. Let's say event A was 0.40, okay? The complement of event A would be 1 minus 0.40 or 0.60, and that's referred to as the complement. Okay, You also have what they call addition laws, and I call it it's the union rule or the addition law. And it's basically where you're looking at multiple events. And eventually what's going to happen is in this case it says special rule of addition. I typically just refer to this as the addition law. And it's where basically you're going to be adding up multiple events. And then eventually they're going to talk about what they call mutually exclusive events. So I'm going to start right here. Notice this one says, what's the probability of A or B? And the basic idea is you just take all the outcomes in A and add those to the probability of B to get, again, I'm going to give you a different symbol, but it's basically the same thing. I'm going to use an elongated U, and I'm going to call this, in quote, I'm going to call this the union rule, okay? Because what's going to happen later on is what if there's some overlap between A and B? How do we deal with that? But for now, if we assume that A and B do not intersect, like for example down here, notice how these events aren't touching each other. If you wanted to figure out the union, all you'd have to do is add them all together to get a total number. That would be called the union. So again, in this example, they're showing you, they wanted you to figure out, okay, what's the union of event A and event C? And so we've got event A and event C, and we've got the probabilities right here. So down here, all they're doing is they're adding these together to get 0.10. That would be either or, which I also call the union. So if we would want to know the complement of this union, and again, A or C, I'm going to say that also represents, I'm going to write it like this, the probability of A union C, okay, which basically means the same thing as that. So let's say, for example, that was equal to 0.10, okay? So if we know that two events are defined as mutually exclusive, which means there's no intersection, they don't share any sample points in common. So let me just kind of give you a visual here. So if I were to draw the Venn diagram, we're basically saying event A and event C. Notice they would not be touching. To get the complement, all you'd have to do is to take this number and take 1 minus 0.10 to get 0.90, because notice there's no overlapping. Now, one more thing. By definition, if two events are mutually exclusive, I'm going to give you another symbol. I like to refer to it as an intersection. Notice in this case, it would be A. I like to use like an arch, okay, C, and I'm going to say that is equal to 0. Okay, so I like to use this in my classes to kind of help people distinguish, to give them a definition, a quantitative definition of mutually exclusive events. So I like to use A, arch C, and I say that's equal to 0, and that's just how I like to define two events that don't have any sample points in common. Okay, now notice we've got a couple of events here. Notice this is A and B, but notice there is some overlap up here. And so here's again is our union. We want to find the union of two events. And notice our formula. And then they like to use A or B, but I like to use A union B. So I hope that doesn't confuse anybody. But notice the way you do it is you take the probability of A plus the probability of B, and you subtract out this where it says the probability of A and B. That's basically everything down here in that intersection. Okay, so I like to rewrite this thing like this. I'm going to say, to get the formula that I would use, I would put it in this format. I would say the probability of A plus the probability of B minus the probability of A intersect B. And again, this means the same thing. And let me give you a couple buzzwords. If you ever see the word both or joint or and, okay, that basically is going to refer to this thing which I call is the intersection, and even down here it's called the joint probability. And so the basic idea is you know, we want to get all the outcomes in both events, but if each event shares outcomes, you don't want to double count. So that comes into this formula right up here. By doing it like this, by subtracting out that intersection, you're not going to count the sample points more than once. Okay, and you know, like I said before, in this case, they had a sample of 200 tourists. Notice there was 120 that went to Disney. There was 100 that went to Busch Gardens. And then notice the 60 that went. Notice you see the word both. They give you the Venn diagram, and of course, they're going to take all these numbers and divide by 200. So if they took, for example, 120 divided by 200, that's going to give you 0.6. That's where they got that number. If they take 100 and divide by 200, that's going to be 0.5. Okay, that's where they got that. And then if they take 60 and divide that by 200, you're going to get 0.30. Okay, so the way I would label this is, and I like to use letters A, B, and C, and so forth. Okay, if I let Disney represent A and Busch Gardens represent B, I would say that the probability of event A would be 0.60. The probability of event B would be 0.50. And the fact that they said both, I'm going to use my intersection. I'm going to say that's 0.30. Here's our both. And I'm just kind of labeling them like that. So if I write it like this down here, notice I would have the probability of A plus the probability of B minus my intersection, which is my union, my addition law, my union. And so down here you'd have again 0.6 plus, it'd be 0.6 plus 0.5, okay? And then you subtract out 0.3. So if you take 0.6 plus 0.5, and then minus 0.3, that would then give you your union answer. Okay, hopefully that doesn't confuse anybody. So they like to use Disney, Busch. They didn't really put it into symbols, but basically, if you can see it right here, this is essentially their calculation they're coming up with. So, and it looks like in this case, I think there was a little typo. So you got 60 plus 50, so that's what, 1.1. You'd have 1.1 minus 0.3. So the answer is actually 0.80. Okay, in this slide, they talk about what they call the special rule of multiplication. And we talk about what they call independent versus dependent events. And the one where they're going to give you right here is, this is going to be what I call the multiplication law for, I'm going to put this on the top here. This is if two events are what are said to be independent. And using my symbols before, I like to use my arch symbol. So the basic idea is to find the intersection or the joint probability is simply to take the probability of A times the probability of B. So it's a multiplication law. Okay, so again, this is referred to again as the joint probability. It's also referred to as an intersection. Okay, that comes up a lot. And then, sometimes you might see again some buzzwords, the words both, or you'll see the buzzword and they like to use and in this particular textbook. Okay, but again, this is how I teach it in my lecture classes. I hope this helps you. I hope it does not confuse you. But this is one of two multiplication laws. The other one, I simply call it the multiplication law for dependent events. Think of this one as the multiplication law for independent events. And basically what it allows you to be able to solve for is sometimes you might need to be able to solve for an intersection as long as you have the probability of each event. You just have to multiply. So in this case, here's an example of their independent test on how to figure out the intersection. Notice it says, what is the probability both? So basically they want you to figure out an intersection, okay? And they got the probabilities of each outcomes. So all they do is they just multiply 0.6 times 0.6. There's your intersection. That's called your joint probability. That's the both, okay? So basically down here you'd say your intersection is equal to 0.36. Okay, and here's the other basic rule, general rule of multiplication. Now, I tend to, whenever I do this in my class, I tend to write out it's called the conditional probability rule first, and then I kind of derive this formula based on that. And what the conditional probability rule goes like this. If you were to take the probability of A given B, that is equal to the intersection divided by the probability of B. So then what they tend to do is, notice, all you have to do is rearrange the formula. If I took this denominator, and if I move that over here, notice what I would come up with. I would have then the probability of B multiplied by the probability of A given B equals my intersection. And that's essentially what they're showing you up there, because this is an intersection right here. And this one is the probability of A times B given A. I just switched it. I said A, B. It's really the same thing. Okay, so this is the multiplication law. I want to make a note. This is for dependent events, which means there is a conditional probability. And the basic conditional probability is always written as like this, something like this. A slash B, which means A given B equals, and again, I like to use my arch, so A intersect B, A and B, divided by the probability of B. So if it helps anybody, the way they kind of wrote theirs up here, they did the probability of B given A. And if I wrote mine out like that, basically the way it would go would be like this. And notice then if I rearrange the formula, I'm going to get exactly what they have up here. I would take the probability of A times the probability of B given A, okay? And essentially that's the exact same thing of what they have up here. And just kind of make a note, that still, this thing right here, still represents your intersection. So I find it helpful to, I really first talk about conditional probability in my class before I actually get into this multiplication rule. But the multiplication rule does come in handy when we get to base theorem, because when we get to base theorem, we're going to need this to figure out the joint, what they call the posteriors and some of the joint probabilities. All right, so it will come in handy later on. So here we got in this particular slide, notice they do talk about what's called a conditional probability. And what that basically means is the probability of one event given another event. So in this case, if it's written like this, where we got probability of A, vertical line B, it's the probability of A given B is occurring. So B event is having some influence, we think, over the probability of the A event. Okay, so this is called a conditional probability. And the basic formula is the probability of A given B equals, and the way they would say is they would say A and B divided by the probability of B. Okay, I like to write it like this, the probability of A given B equals, and I like to use this as my symbol, so I'm going to say A arch B divided by the probability of B. Okay, now one more thing, because later on we will get into, I'll show you some tables and so how do you calculate these using a table. Make a note that this joint, this numerator, is also again referred to as what they call the joint probability. And I want you to also make a note, this denominator, I want you to write the word margin, okay, because the denominator is sometimes referred to as the margin. So anytime you're doing conditional probability calculations, you can often refer to it as what's called a ratio of the joint probability divided by the marginal probability. So it's always going to be a joint or intersection divided by a margin. And I think this will come in handy later on when I show you how to use some of the tables. Okay, so down below in this particular table, you can see they call these a contingency table. And the way these tables tend to work is that I'm going to circle a couple things. If I circle everything here, notice I'm circling everything in the inner part of the table where you've got one column that says movies attended, okay, in this row, and then you've got men and women. So I'm circling everything in here that's in the body of the table. I'm going to refer to those as a joint probability, or I want you to think of they're basically everything in there is an intersection, okay? Now, the other thing is, notice I'm going to draw a line here and a line there. These total numbers right here, the 60, the 70, and the 20, and the 70 and the 80, guys, that's going to represent what I like to refer to as the margin, because everything there's a total in the margins, okay? And then finally, you'll notice the way these work is you should be able to add across and down and come up with this total. Eventually, you want to lead to that total, which is 150. So for example, if you take 20 plus 40, you get 60. If you take 40 plus 30, you get 70. And of course, 10 plus 10 gets you to 20. Now, if I added them down, you get 20 plus 40 plus 10 gets you to 70. 40, 30, 10 gets you to 80. And then watch this. 70 plus 80 gets you to 150. 60 plus 70 plus 20 also gets you to 150. So everything in the lower right-hand corner of these tables always is the total of that's the total number in your sample. Everything needs to add up to that lower right-hand number. But these are all called contingency tables. So if you were using this table to get some probabilities, and the question was, what's the probability that a person didn't attend any movies? So that means both men and women. You're talking about the margin. So the margin in this case is 60. And to convert that into a probability, you would just divide that by 150. And so the answer would be 0.40. Okay, so notice in this example, it says, what's the probability that a person attended 0 movies or is male? So anytime they're going to ask for the or, that's going to be a union, okay, or an addition. So basically, we want everybody who was at 0, so that looks like that's 60. But the also was asking for it once all the males, which is 70. Okay, so the question is okay, we've got this category, we've got this margin, and we've got this margin, but we also have the possibility we want to figure out, we just want the men, which we got to include this little intersection up there. Okay, so the basic formula again is going to be the probability of A plus the probability of B minus the probability of any intersection. Okay, because notice there is an intersection here we don't want to double count because there's some men. We got the 0 attendant, which does include some women, and we also have, in this category, the case of the men. So down below you can see the calculation. Notice they took the 60 over 150, they took the 70 over 150, so that's A or B, and then notice how they subtracted out the intersection. They put that right there and they came up with 0.733. So basically, here's your probability of A down here. That's the probability of B, and then we can look at that as the probability of the intersection. So the way you can recognize if they're asking for the addition law is if it says or, either or, that would be kind of like a big clue that that's what they want you to calculate. And in this case, they're giving you an example of a condition. And so how you want to approach this, it says, what is the probability that a person attended 0 movies if that person is male? So I want to make a point that that's what we call that's the given you're a male. And the given is always going to be what they call the margin. So if I go to the male column, the margin is 70, okay? So the first step is we know that's going to be your denominator, okay? Now, if I go to my basic conditional probability formula, the idea is A given B equals an intersection, right, divided by the probability of B. And I told you before, it's always going to be what's called your joint divided by the margin. So the fact that we already figured out that the margin is the given, that's the male, that's going to be 70, okay? And a conditional probability is always an intersection over margin. I simply want to know which of these categories do I want to look at the intersection. And I want this category, the 20, because that intersects with 0. So that will be my intersection. So all you got to do is take 20 divided by 70, and they're showing you this right there. You get the 0.286. Okay, so going back to my little terminology here, think of conditional probabilities as it's always going to be some sort of joint probability divided by a margin. In this example, the margin was male. They could have changed it and they could have said women, and you just have to, you'd have to switch the margin out. So, but the way they've worded this, if or given, is always going to be the denominator, which is said to be the margin. So in this particular example, they're wanting you to apply the multiplication rule for dependent events. And essentially what that would be doing, if I wrote that one up again, so let me write the basic formula. If you took the probability of A given B equals an intersection, okay, divided by, for example, the probability of B. Remember, this probability of B, everything in the denominator represents what they call a margin, okay? So in this case, it looks like they're wanting male and attended 0 movies, okay? So we know that this particular, look at the margin, is 70, right? So we know we're focusing on that particular margin. And so we would need to know what is that probability. So obviously that would be 70 over 150, okay? So that would give us our margin. And in fact, let me write this out over here. So for example, if we took the probability of this margin, and then we need to multiply by the condition, okay, which is the dependency, and in that case, it's going to be the 20. The 20 is going to represent the condition. So notice you'd have to take that, okay, that conditional probability is that divided by 70. And so basically, when you multiply these out, that's going to give you what they call your intersection, in this case for dependent events. And they're showing you the calculations down here. Notice they took 70 divided by 150 multiplied by 20 over 70 to get the dependent intersection, which in this case would be 0.133. Okay, the last thing in the chapter is what they refer to as Bayes' theorem, and this is the basic formula. And you'll notice this is basically based on dependent condition type of rules. And notice you got the probability of A times the probability of B given A. Guys, that's really just your conditional probability formula right there, okay? But I want you to think of this, really, in fact, that represents what's called your joint probability. And so because we're going to look at multiple case scenarios, notice that it's like saying this is the calculation on how to get an intersection for for two dependent variables, okay? And everything here in the denominator is simply adding up all the different joints of the different cases you're going to look at. So later on, what's going to happen is I'm going to show you how to do this in what they call the tabular approach, where what's going to happen is we're going to have one column which we're going to label as what's called your prior probability. We're going to then have your conditional probability, okay? That'll be in the problem. And then what's going to happen is I'm going to label this one as your margin. We're going to call that as a marginal probability. We're going to multiply that by the conditional probability. And then eventually what's going to happen is that's going to give us the joint probability. And so we typically label these as A1. We'll label this as B given A1. And when we multiply that, that's going to give us our joint. And essentially, that's what this formula up here is going to be doing, okay? So then what we'll do is once we set these tables up, the last column is actually what they call the posterior probability. And all that's going to do is that's going to take everything in this column when we set it up, and we're going to have to add up everything in the column, and we're going to take each of the joint probabilities, and we're going to divide by the sum of the joint probabilities, and we're going to put it in this column called the posterior. And then this posterior, then we're going to relabel that as A given B, okay? So just kind of use this kind of when we get started with it, but we're going to do everything here in a tabular format. I think when you first look at this thing, it looks kind of scary. It's not really going to be that bad because I'm going to give you some examples later on to show you how we set up the table. And all I'm going to say on these is they're giving you basically 3 events, and notice they've got the prior probabilities labeled, and then they've got additional information and so forth. All I'm going to say about this is you can look at this in the next slide. I'm going to have some other postings, some other PowerPoint presentations and videos giving you, I think, the tabular approach on how to solve for some of these, and I think you'll find that advantageous and easier to learn.